January 5, 1943, the South Pacific, near Guadalcanal. A Japanese Aichi D-3A dive bomber initiates an attack run on the American cruiser USS Helena. The ship's gunners return fire with a 5-inch artillery shell, but the trajectory is slightly off. It is on course to miss the aircraft by dozens of feet. By the established mathematical laws of anti-aircraft warfare, the bomber should easily survive and complete its strike. Instead, without ever making physical contact, the shell suddenly detonates mid-air at the exact moment it passes the plane. The blast instantly shreds the aircraft, sending it plunging into the ocean. That seemingly impossible kill in the South Pacific was not a fluke. It marked the highly classified combat debut of the proximity fuse. This technology was an asset guarded so closely by the Allied High Command that its security protocols rivaled those of the atomic bomb. The weapon fundamentally rewrote the rules of engagement, but it forces a staggering engineering question. How exactly did a team of civilian scientists manage to shrink a functioning radar transmitter and receiver until it could fit inside the nose of a spinning 5-inch artillery shell? Even more baffling, how did they engineer delicate glass vacuum tubes, components as fragile as a standard light bulb, capable of surviving the brutal 20,000 G-force acceleration of being fired from a naval cannon? It was a desperate scientific gamble to take a physical impossibility and transform it into a mass-produced, battle-ready weapon. The development effort required overcoming extreme physics and massive manufacturing hurdles under the crushing time pressure of a global war. But to truly grasp the magnitude of this technological miracle, and why the United States military poured massive resources into solving it, we first have to examine the grim, highly inefficient reality of conventional anti-aircraft warfare in the early 1940s. By the summer of 1940, the speed and maneuverability of combat aircraft had fundamentally outpaced the technology designed to destroy them. If you were an anti-aircraft gunner trying to shoot down a bomber flying at 300 miles per hour, at an altitude of 10,000 feet, you were not truly aiming at the aircraft. You were aiming at a mathematical prediction of where that aircraft would be by the time your shell reached that altitude. It was an incredibly complex calculus problem executed under the deafening, chaotic conditions of combat. The standard ammunition of the era relied on mechanical time fuses. Before a shell was loaded into the breech of a gun, an artilleryman had to manually set a highly complex internal clockwork mechanism. This timer dictated exactly when the shell would detonate after leaving the barrel. To get a kill, the timing had to be absolutely flawless. If the fuse was set for 14.2 seconds, but the shell reached the target area at 14.5 seconds, the explosion would happen in empty airspace. The lethal radius of a standard 5-inch anti-aircraft shell was roughly 50 feet. A miscalculation of a fraction of a second, a slight variation in muzzle velocity, a shift in wind speed, or a sudden evasive maneuver by the enemy pilot meant the shell missed completely. The sheer inefficiency of this system was staggering. During the intense aerial bombardments of the Blitz over Britain in late 1940 and early 1941, British anti-aircraft batteries were firing blindly into the night sky, relying on searchlights and primitive ground radar just to point the guns in the general direction of incoming Luftwaffe formations. Statistical analysis from that period revealed a crushing reality. It took an average of roughly 20,000 artillery shells to bring down a single enemy bomber. The skies were filled with exploding flak, but it was essentially a giant, lethal lottery. Naval warfare faced an even more desperate scenario. A ship at sea was a confined, isolated target. If a squadron of dive bombers or torpedo planes broke through the combat air patrol, the ship's survival depended entirely on its anti-aircraft batteries. But the mechanical time fuses required constant, frantic readjustment as the enemy planes rapidly closed the distance. Gunners were forced to rely on contact fuses, shells that only detonated upon a direct physical strike against the aircraft. Hitting a fast-moving, erratic target with a direct artillery strike was virtually impossible. The Allied military apparatus recognized that unless they could drastically improve the hit ratio, their surface fleets and vital supply convoys would be systematically dismantled from the air. The theoretical solution was obvious to military engineers across the globe: a smart shell. a projectile equipped with an internal sensor that could detect when it was in lethal range of an enemy aircraft and detonate itself automatically. No more manual timers. No more calculating exact lead distances for altitude. If the shell simply flew close to the target, the proximity sensor would do the rest. But conceptualizing a smart weapon and physically building one were two entirely different realities. In 1940, the only technology capable of detecting an aircraft in flight, even at short distances, was radar. And the radar systems of 1940 were industrial behemoths. The early British chain-home radar stations required massive steel towers and entire buildings packed with power generators, cooling systems, and massive arrays of vacuum tubes. Even the cutting-edge radar sets being installed on naval cruisers were the size of small rooms, weighing thousands of pounds. To make a proximity fuse work, engineers would have to take a functioning radar transmitter, a receiver, an amplifier, and a power supply, and shrink all of it until it could fit into a space roughly the size of a standard milk bottle, specifically the nose cone of a 5-inch artillery shell. To traditional military contractors and ordnance departments, this proposition bordered on science fiction. The miniaturization required was beyond anything the electronics industry had ever attempted. And even if they could somehow shrink a radar set to fit inside a shell, they faced an insurmountable wall of physics. Artillery shells are not gently launched into the sky. When a 5-inch naval gun fires, the explosive propellant inside the casing detonates, generating catastrophic pressure. The projectile is violently shoved out of the steel barrel, accelerating from 0 to over 2,600 feet per second in a matter of milliseconds. The internal components of the shell are subjected to an acceleration force of 20,000 Gs. That is 20,000 times the normal force of gravity. Simultaneously, the rifling inside the gun barrel forces the shell to spin at nearly 30,000 revolutions per minute to stabilize its flight path. The core components of any radar system in 1940 were glass vacuum tubes. These were incredibly delicate electronic valves, built with fragile wire filaments and glass envelopes, essentially as fragile as domestic light bulbs. Dropping a standard vacuum tube on a concrete floor would shatter it. The idea of packing a dozen of these glass tubes into a steel shell, blasting them out of a cannon at 20,000 Gs while spinning them at thousands of revolutions per minute, and expecting them to survive and function flawlessly was considered absurd. Ordnance experts mathematically proved that the glass would pulverize, the filaments would snap, and the miniature batteries would be crushed under their own weight. The military engineering establishment looked at the physics, looked at the limitations of 1940 manufacturing, and quietly concluded that a radar-guided proximity fuse was an impossible dream. If the Allies were going to break this technological wall and change the mathematics of anti-aircraft warfare, the solution would not come from the traditional military-industrial complex. It would require an entirely different approach, driven by an unorthodox, highly secretive group of civilian scientists operating far outside the standard chain of command. That unorthodox approach began in August 1940 with a clandestine unit known simply as Section T, operating under the National Defense Research Committee and later formalized as the Applied Physics Laboratory at Johns Hopkins University. The group was assembled by an experimental physicist named Merle Tuvey. Tuvey and his civilian researchers were not bound by rigid military doctrine, and they refused to accept that glass was inherently too fragile for artillery warfare. Yet instead of spending years trying to invent an entirely new, indestructible synthetic material from scratch, Section T made a radically pragmatic decision. They looked directly at the civilian commercial market. At the time, the only mass-produced miniature electronic valves in existence were sub-miniature vacuum tubes manufactured for wearable civilian hearing aids. Companies like Raytheon and Sylvania were building these tiny, thumb-sized glass components for quiet, domestic use. To a traditional naval ordnance engineer, inserting a fragile hearing aid part into an explosive artillery shell was insanity. But to Tuvey, it was simply a shock mitigation puzzle. Before taking their concepts to a live firing range, Section T subjected the commercial tubes to brutal, low-tech stress tests. Scientists embedded the tiny glass components inside solid lead blocks and systematically dropped them off the roofs of tall buildings and down elevator shafts onto solid steel plates below. By slicing open the deformed lead casing after impact, they could perform a precise forensic analysis on the shattered electronics. The data revealed a critical surprise. The outer glass envelope was rarely the first element to fail. Instead, the microscopic internal wire filaments were snapping under the sudden deceleration, and the internal mounting brackets were collapsing inward under their own weight. Armed with this knowledge, Tuve's team collaborated with vacuum tube manufacturers to reinforce the internal wiring and slightly thicken the glass walls. But the decisive breakthrough came from how those modified tubes were physically secured inside the projectile. The researchers realized that any air gaps or traditional mechanical springs would allow catastrophic micro-vibrations to tear the circuitry apart during a cannon launch. Their solution was a technique called potting. They placed the delicate electronic components inside the shell's nose cone and poured molten microcrystalline wax, mineral oil, and specialized plastic resins directly over them. Once hardened, the electronics were entirely encased inside a solid, shock-absorbing block. The potting compound distributed the immense kinetic forces evenly across the entire surface area of the glass, preventing the internal structures from flexing or snapping. When Section T finally took these handcrafted prototypes to a naval proving ground and fired them from 5-inch guns, the results stunned military observers. Ground radio monitors tracked the shells in flight and confirmed the unthinkable. The glass tubes were surviving the violent blast and transmitting a continuous, steady signal while spinning through the sky. Physics had been conquered in the laboratory, but proving the concept was only half the battle. Now, the United States had to figure out how to take a hand-poured, custom-calibrated scientific prototype and secretly manufacture millions of them on industrial assembly lines, all without the Axis powers discovering what was being built. Transitioning from a hand-poured, custom-calibrated scientific prototype to the industrial mass production of millions of units presented a logistical nightmare that bordered on the impossible. The United States government had to mobilize civilian manufacturing sectors that had never before handled high-explosive ordnance, let alone top-secret military electronics. By the end of 1942, the project had expanded far beyond the Applied Physics Laboratory, pulling in massive industrial contractors like the Crosley Corporation in Cincinnati, Sylvania Electric in Pennsylvania, and RCA. But building a radar set that could fit inside a 5-inch artillery shell was not a matter of simply scaling down standard radio components. It required an entirely new discipline of micro-manufacturing. The assembly lines of these civilian plants were rapidly transformed. The military heavily recruited women specifically for their professional backgrounds in watchmaking, jewelry repair, and fine textile embroidery. These workers possessed the extreme manual dexterity required to manipulate microscopic wire filaments and solder connections that were barely visible to the naked eye. Working under magnifying glasses in meticulously clean rooms, they assembled the miniature amplifier circuits, the oscillator tubes, and the thyrotron trigger valves. The secrecy surrounding the operation was absolute and heavily compartmentalized. The women on the soldering lines were told they were building parts for standard radios. Workers constructing the heavy steel casings in different plants had no idea what electronics were being slotted into them. Final assembly was isolated, heavily guarded, and restricted to a select few with top-tier security clearances. Yet, even with perfect assembly and Tuve's shock-absorbing potting wax, the engineers faced another critical hurdle: power. A proximity fuse needed a battery to operate its internal radar, but standard dry-cell batteries of the era degraded quickly. If a batch of fuses sat in the sweltering, humid ammunition magazine of a naval cruiser in the South Pacific for 6 months, standard batteries would lose their charge. An artillery shell with a dead battery was just a heavy piece of metal. The solution was an act of controlled violence engineered directly into the mechanics of the projectile. Scientists at the National Bureau of Standards invented what became known as a reserve wet battery. It was an electrical power source that literally did not exist until the exact fraction of a second the gun was fired. Inside the battery casing, the engineers placed a fragile glass ampule filled with highly corrosive chromic acid, surrounded by dry carbon and zinc plates. As long as the shell was in storage, the battery was completely inert. But the moment the naval gun fired, the brutal 20,000 G-force of the launch intentionally shattered the glass ampule. Simultaneously, the rifling in the gun barrel forced the shell to spin at tens of thousands of revolutions per minute. The intense centrifugal force of that spin drove the unleashed chromic acid outward, violently forcing it between the carbon and zinc plates. In the span of a few milliseconds, the chemical reaction was ignited, electrically waking up the radar system just as the shell cleared the muzzle of the gun. By late autumn of 1942, the factories had achieved the impossible. They were mass-producing ruggedized, microscopic radar transmitters powered by shock-activated chemical batteries. To maintain the veil of absolute secrecy, the Ordnance Department issued a deliberately misleading classification. The new weapons were officially designated as VT fuses. The letters stood for variable time, a mundane psychological misdirection designed to convince any Axis spy monitoring supply manifests that the United States had simply built another standard mechanical clockwork timer. Under armed Marine Guard, the first mass production run of the VT fuses was transported across the continental United States on heavily secured trains to the Mare Island Naval Shipyard in California. From there, they were loaded deep into the holds of ammunition ships and sent westward, directly into the bloodiest theater of the naval war, Admiral William Halsey's South Pacific Command. The American fleet in the Pacific was severely battered. The grueling, attritional naval battles around Guadalcanal and the Solomon Islands had taken a heavy toll on cruisers and destroyers. Japanese land-based bombers and carrier strike groups were highly experienced, aggressive, and highly effective at penetrating American defensive parametric anti-aircraft fire. When the first crates of VT ammunition were unpacked aboard cruisers like the USS Helena in early 1943, the gunnery crews were issued strict new protocols. They were handling technology that cost roughly $73 a shell, an astronomical sum for a single piece of disposable ammunition at the time, equivalent to a small fortune for a sustained barrage. But the fuse did not operate in a vacuum. It was the lethal final component of a highly sophisticated, integrated weapon system. The ships utilizing the new shells were equipped with the Mark 37 gunfire control system, tied to the latest FD tracking radars. The ship's main radar would detect the incoming Japanese aircraft miles away. The analog fire control computers deep in the hull of the ship would calculate the target's speed, altitude, and bearing. The 5-inch guns would automatically slave to the computer's coordinates, tracking the invisible enemy through clouds or the dead of night. In the past, the gunner had to guess the mechanical fuse setting and hope the mathematics held true. Now, the crew simply loaded the VT shell into the breech and pulled the firing lanyard. For the first second of flight, the proximity fuse remained dormant, a safety mechanism ensuring the shell did not detect the ship's own rigging or nearby friendly vessels and detonate prematurely. Once it cleared a safe distance, the internal thyrotron valve opened the circuit. The shell became a live, broadcasting radio station, screaming through the sky. It emitted a continuous, cone-shaped, continuous wave radio signal forward along its flight path. The immediate combat impact fundamentally altered the tactical mathematics of naval warfare. Prior to the introduction of the VT fuse, statistical analysis indicated that Pacific Fleet anti-aircraft batteries required thousands of rounds of standard ammunition to register a single confirmed kill on a fast-moving Japanese bomber. During operations with Task Force 18 and Task Force 67 in early 1943, the kill ratio violently shifted. The number of shells required to destroy an aircraft plummeted into the low hundreds, and in optimal conditions to less than 100 rounds per kill. The probability of destroying an incoming threat increased tenfold almost overnight. The true terror of the proximity fuse, however, was not just its sensor, it was the geometry of its detonation. When the continuous radio wave emitted by the shell struck the aluminum fuselage of a Japanese aircraft, it reflected back to the microscopic receiver inside the shell's nose. The internal amplifier read the returning signal, and as the shell closed the distance, the amplitude of that returning wave spiked. The circuit was hardwired to recognize a specific threshold, a mathematical point that corresponded to a distance of roughly 70 feet from the target. When the signal hit that peak, the electronic switch tripped. The ensuing explosion was not designed to hit the aircraft with the shell itself. The detonator ignited the high explosive charge, violently rupturing the heavy steel casing of the 5-inch projectile. The physics of the blast, combined with the forward momentum of the shell traveling at over 2,000 feet per second, forced the jagged steel shrapnel outward and forward in a rapidly expanding, highly concentrated cone of fragmentation. A Japanese pilot did not need to be struck by the artillery shell. He simply had to fly anywhere near it, and his aircraft would instantly fly into a supersonic wall of red-hot steel, shredding engine blocks, severing control cables, and igniting fuel lines. From the perspective of the Imperial Japanese Navy Air Service, the sudden shift in American anti-aircraft lethality was inexplicable. The Japanese aviators operating out of the massive fortress base at Rabaul were combat veterans. They had survived the skies over Midway, the Coral Sea, and the grueling Guadalcanal campaign. They intimately understood the mechanics of standard Allied anti-aircraft fire. A veteran pilot knew that mechanical flak was predictive. If he saw the black bursts of explosions appearing at his altitude, he knew the enemy gunners had calculated his speed and trajectory. The countermeasure was standard doctrine: aggressively change altitude, drop the nose, alter the heading, and completely invalidate the mechanical timer settings of the shells already in the air. But in early 1943, these proven evasive maneuvers suddenly stopped working. Intercepted radio chatter and surviving Japanese after-action reports revealed a profound, creeping dread spreading among the bomber squadrons. Pilots reported that American flak was no longer bursting randomly in the sky or trailing behind them. The explosions were tracking them. No matter how violently a Mitsubishi bomber threw itself into a dive, or how erratically an Aichi dive bomber jinked through the clouds, the American shells seemed to detonate perfectly alongside their cockpits with impossible precision. Without understanding the technological leap that had occurred, Japanese intelligence analysts and squadron commanders drew the only logical conclusions available to them. They assumed the Americans had developed impossibly precise optical rangefinders, or that a new generation of preternaturally gifted gunnery officers had arrived in the theater. They had no conceptual framework to even imagine that the Americans had shrunk a radar station and placed it inside a spinning bullet. Crucially, the Japanese had no way to investigate the phenomenon. The greatest ally of Allied secrecy in the Pacific theater was the ocean itself. In standard land warfare, if a new type of artillery shell fails to explode, it buries itself in the dirt. It becomes a dud, waiting for enemy ordnance disposal teams to dig it up, dismantle it, and study its internal mechanics. But in the naval battles of the South Pacific, a dud shell, one where the glass ampule failed to shatter, or the wire filament snapped under the extreme G-force, simply splashed into the deep water. It sank thousands of fathoms down into the abyss, taking the highly classified circuitry with it. The ocean completely swallowed the forensic evidence. The Japanese were dying in unprecedented numbers, facing a weapon they could neither understand nor capture. But this overwhelming, unmitigated combat success immediately birthed a terrifying new paranoia among the Allied High Command in Washington. When the combat data from Admiral Halsey's fleet reached the desk of Dr. Vannevar Bush and the Joint Chiefs of Staff, the mood was not merely celebratory, it was deeply anxious. The VT fuse was performing far beyond even the most optimistic laboratory projections. It was proving to be a definitive war-winning technology, and because of that immense power, it became a strategic liability. The highest levels of military intelligence understood a grim reality. The Axis powers did not need to independently invent a proximity fuse. They only needed to realize it was possible. German scientists in particular already possessed highly advanced theoretical physics, sophisticated radar networks, and precision manufacturing capabilities. If the Germans or the Japanese ever captured a single intact dud shell, their engineers would instantly recognize the function of the miniature vacuum tubes and the thyrotron circuits. The secret of the reserve battery and the potting wax would be laid bare on an inspection table. If Nazi Germany reverse-engineered the proximity fuse and adapted it to their dreaded 88mm anti-aircraft guns, the strategic balance of the war in Europe would instantly collapse. The Allied strategy for defeating Germany relied entirely on the combined bomber offensive. Every day, the United States 8th Air Force sent hundreds of heavy bombers deep into hostile territory to cripple German industrial centers. These bomber streams were already suffering horrific casualties from standard mechanically fused German flak. If the Luftwaffe anti-aircraft batteries were suddenly equipped with radar-guided smart shells, the B-17 and Lancaster formations would be annihilated. The skies over Europe would become a slaughterhouse, making the strategic bombing campaign mathematically impossible to sustain. Driven by this existential threat, the Joint Chiefs of Staff drafted a draconian, non-negotiable directive that altered the application of the weapon for years. The proximity fuse was classified with restrictions rivaling those placed on the Manhattan Project. The order mandated that the VT fuse could only be issued to naval vessels, and it could only be fired over deep, open water. It was absolutely prohibited from being fired at terrestrial targets or over land masses, where a dud might be recovered by enemy ground forces. This sweeping strategic restriction created an agonizing moral and tactical paradox on the ground. As the United States Army and British forces pushed into the grueling, bloody infantry campaigns of North Africa, the invasion of Sicily, and the brutal crawl up the Italian peninsula, they faced relentless Axis artillery and devastating close air support from Luftwaffe Stukas. The Allied infantry commanders desperately needed the devastating airburst capability of the proximity fuse to shatter German troop concentrations and clear the skies over their beachheads. Yet they were systematically denied access. Millions of the most lethal artillery shells ever manufactured sat safely in the locked magazines of naval destroyers offshore, held back by a strategic calculation made thousands of miles away. Men bled and died in the mud of Italy, fighting with outdated mechanical fuses, directly paying the price in blood to protect a technological secret they didn't even know existed. This draconian restriction did not just punish the Army in Europe. Across the Pacific theater, United States Marines conducting grueling amphibious assaults faced the exact same institutional wall. When American forces stormed the heavily fortified beaches of Tarawa and Peleliu, they were pinned down by deeply entrenched Japanese defenders. An airburst artillery shell capable of detecting the ground and detonating precisely 30 feet above a trench, showering open positions with lethal fragmentation, would have neutralized those defenses in minutes. The naval destroyers providing direct fire support just offshore had thousands of those exact proximity fuses sitting in their magazines. But the standing orders from Washington remained absolute. Firing a VT fuse over a landmass was strictly prohibited. If a single dud buried itself in the volcanic ash, Japanese intelligence could recover the technology and transmit the blueprints to their German allies. Consequently, naval gunners were forced to use conventional impact fuses that buried themselves harmlessly in the sand, while Marines suffered catastrophic casualties yards away. It was a brutal institutional calculation. The combined chiefs of staff, paralyzed by the fear of a reverse-engineered fuse decimating Allied bomber fleets, accepted severe infantry losses as a necessary strategic tax. For nearly 2 years, the most devastating tactical advantage in the American arsenal remained quarantined over deep water. Field commanders in France submitted urgent requisitions for the rumored smart shells to break German counterattacks, but every request was systematically intercepted and denied by the War Department. But strategic red lines only hold until desperation shatters them. By the bitter winter of 1944, the global conflict shifted violently. In the freezing Ardennes forest, a massive, unpredicted German armored offensive tore through American lines, triggering the catastrophic Battle of the Bulge. Allied infantry were suddenly surrounded and desperate for any advantage to halt the advancing German columns. Simultaneously, half a world away, the naval fleets found themselves facing a terrifying evolution in Japanese warfare. The enemy was no longer simply dropping bombs. They were turning the aircraft themselves into manned missiles. A synchronized, dual-hemisphere crisis had arrived. Facing a collapsing European front line and a devastating new suicide tactic at sea, the Supreme Command in Washington was forced into a corner. Protecting the absolute secrecy of the proximity fuse was no longer viable. The ban finally had to be lifted. The breaking of that absolute restriction culminated in the spring of 1945, specifically during the massive, grueling amphibious assault on Okinawa. The United States Navy had parked the largest armada in human history off the coast of the island. But this immense concentration of steel and manpower was completely exposed to a terrifying evolution in Japanese strategy. The Imperial Japanese military, acutely aware that they could no longer compete with American industrial output or standard tactical maneuvering, fully committed to the kamikaze. These were not traditional combat pilots intending to drop ordnance and return to base. They were massed waves of dedicated suicide pilots, flying aircraft packed tightly with high explosives, ordered to plunge their planes directly into the decks of American warships. The sheer psychological and tactical pressure this placed on the fleet was unprecedented. A kamikaze pilot did not need to survive to be effective. He only needed to reach the ship. If an American anti-aircraft gunner managed to damage the engine or shred the wing of an incoming suicide plane using standard mechanical flak, it often wasn't enough. The forward momentum of the crippled, flaming aircraft could still carry it directly into a destroyer's bridge or an aircraft carrier's flight deck, causing catastrophic casualties. The traditional requirement of merely damaging an enemy aircraft was obsolete. The American gunners now had to instantly and completely disintegrate the incoming plane mid-flight. With the deep water ban officially rescinded, the vast magazines of VT proximity fuses were unleashed. The airspace surrounding the invasion fleet was violently transformed as hundreds of Japanese aircraft swarmed the horizon, executing steep dives and erratic, desperate maneuvers to evade the outer fighter screens. They plunged into the naval perimeter. But instead of flying through predictive bursts of standard flak, they flew directly into an automated wall of targeted shrapnel. The radar-guided shells operated with an inescapable cold mathematics. The gunners simply tracked the incoming suicide planes and fired into their general flight path. The miniature vacuum tubes inside the shells instantly registered the reflection of the Japanese fuselages. At the precise optimal distance, the thyrotron circuits tripped, detonating the heavy steel casings and expanding a concentrated, high-velocity cone of fragmentation directly into the path of the aircraft. The proximity fuse fundamentally negated the sheer human dedication of the kamikaze pilots. A pilot could execute a flawless evasive maneuver, commit entirely to the dive, and accept his own death, only to be violently shredded yards from his target by a shell that had autonomously calculated its own lethal intercept point. The battle became a stark, brutal demonstration of industrial and electronic supremacy overriding sheer human willpower. The human element of flying the plane, no matter how committed, could no longer bypass the automated precision engineered into a spinning artillery shell. This brutal reality brings us exactly back to that January afternoon in 1943, and the lone Japanese dive bomber aligning its sights on the USS Helena. When that first proximity-fused shell detonated perfectly in midair, it did not just destroy a single Aichi D3A. It signaled a permanent, fundamental shift in the mechanics of combat. The desperate scientific gambles, the shattered glass in Merle Tuvey's drop tests, the specialized potting wax, and the millions of microscopic solder joints assembled by women in civilian factories had culminated in a weapon that broke the old laws of physics and probability. However, it is a historical fallacy to claim that this tiny radar transmitter won the Second World War single-handedly. The VT fuse was not an isolated magic bullet. It was completely inert without the gargantuan American logistics chain required to manufacture and transport millions of units across the Pacific. It relied entirely on the massive, room-sized shipboard search radars to initially detect the threats, the complex analog fire control computers deep in the naval hulls to track them, and the sheer, overwhelming volume of 5-inch artillery fire the Allied fleets were capable of projecting. It was merely the lethal tip of a much larger, highly integrated technological spear. But what those microscopic vacuum tubes did prove was that the era of mechanical guesswork was definitively dead. For the first time in history, anti-aircraft warfare was no longer a deadly lottery, constrained by human reflexes, manual clockwork timers, and the blind hope that an artillery shell and a fast-moving target would miraculously occupy the exact same coordinate in an infinite sky. The proximity fuse erased that reliance on blind luck. It proved that raw computing power, encapsulated within ruggedized, miniaturized electronics, could effortlessly outmatch both the fastest evasive maneuvers and the most dedicated human pilots. The technology engineered inside those spinning artillery shells fundamentally altered the baseline relationship between the weapon and its target. It established a cold, unbreakable precedent for the future of combat that extends far beyond the Second World War. The true revolution forged by those civilian scientists was not about building a larger bomb or a faster artillery shell, but about delegating the critical moment of decision to a microscopic circuit. Ultimately, the story of the proximity fuse proved that in the brutal arithmetic of modern warfare, the most devastating component is no longer the raw, high explosive packed inside the steel casing. Instead, the ultimate arbiter of life and death is the invisible, calculating electronic brain hidden within.